Hello again, and after the whopping success of the inaugural video on directing groups, which, as of this morning, had a total amount of views of, drumroll please, 14. Yes! Thank you everyone for watching. I thought we'd do another one on KC, seeing as though we're covering that in school at the moment. So, I'm going to look at what KC is, going to talk a bit about how it works, going to have a look at how we generate an expression of KC, how we then work out what the units are, and then just look at some of the application, how we're going to apply what we know to some questions. So what is KC and how does it work? Well, KC, and we'll come on to KP, but not today, because my son's probably going to wake up in a bit and I'm going to have to go up and look after him. So we're just going to have a look at KC. And it applies to KP as well, but it's ratios. All it is looking at the ratio. So if we look at the reaction, A plus B reacts to make C and D. Well, let's put some, balance this out. So A, B, K, and D. If we want to go really primary school, just helps us out to visualize it. And yes, I know those of you that have read the textbook, well, that looks awfully familiar, Mr. Jenkins. It does, yes, you're right, but it's a nice way of just generalizing it to make it easy to access to start off with. So KC is the ratio between the products and the reactants, and that's it. That's what this little infographic down here is all about. So let's have a look at it. The KC equilibrium constant is products C times by D over the reactants A times by B. That's not it. These little numbers here, or these little letters, are significant. Part of the whole stoichiometry, the balancing of the equation, we need to incorporate that in. So make sure that the C is to the power of K, D is to the power of D, A is to the power of A, and B is to the power of B. We need to get in those indices, and if we don't get those indices in, it's just not going to work. So we've now got a ratio of products to reactants. And that's what it's all about. When we come into talking about changing conditions later on in the course, and that's not for this video, that will be for another video. When we talk about how we change conditions, that links in very nicely to ratios. And that's why, no, Mr. Jenkins, don't get ahead of yourself. We'll come to that later. So, ratios. KC. KC is an indication of where that equilibrium lies. Does it lie more towards the products, or does it lie more towards the reactants? If we've got a very, very small KC value, below 1, that means that we have got loads more reactants. The equilibrium, or the balance, the ratio, is significantly on the reactant side, which means that we have loads and loads of reactants, i.e. we've got a bigger number underneath a little number, or a littler number. If KC is 1, it means that we have got equal amounts of products to reactants. They're equivalent. And if we've got KC is greater than 1, it means that we have got equilibrium lying predominantly on the product side. So we've got a larger value for the products, i.e. the big number, divided by the little number. So we've got more products. And that's it. That's what KC is all about representing. It's telling us what that ratio is. Have we got more products or less products? More reactants or less reactants? Where does that equilibrium lie? So let's put that into let's put this into a bit of practice then. We've got space there. Yeah, we've got some space here. So let's take a reaction. W plus X, which is the equilibrium form 3y. Kc for this would be concentration of y to the power of 3 divided by concentration of W times by the concentration of X. And that's our expression. Later on, we will have a look at how we just substitute values into that to be able to calculate C. What we've not talked about yet, and if you're just doing the AS course, this is kind of where it stops. If you're going on into doing A2, we're going to be expected to work out what the units are. And units is really important because we are dealing with concentrations here. So we're going to need to start having a look at those concentrations and how they then cancel out. So we have got moles per decimeter cubed. We've got that to the power of 3 divided by moles per decimeter cubed times by moles per decimeter cubed. Now what I'm going to do, I'm just going to rub out the brackets. So we've got to the power of 3, so we've got moles per decimeter cubed times by moles per dm cubed. Ooh, I might run out of space here. Let's go do here. Mole dm cubed. So we've got moles per decimeter cubed times by moles per decimeter cubed times by moles per decimeter cubed over moles per dm cubed times by moles per dm cubed. So what we can do is cancel them out. That and that cancel out. That and that cancel out. So our units for this Kc are moles per decimeter cubed. That was a nice easy one. We'll look at a different one below where it's not quite as simple. So shall we take a new equation? A plus 3b reaches equilibrium to form C and D. Kc for this would be, and feel free to pause it, have a go at writing the expression yourself, and then you can unpause it and see if you got it right. Concentration of C times by concentration of D divided by concentration of A times by concentration of B to the power of 3. Now, I know what you're thinking. Mr. Jenkins, you numpty, you've just given yourself a whole load of writing to do. You're absolutely right, I have, but I thought it would be a nice visual to help us here. So, zoom in, and I'm going to have to do a bit of smaller writing. So we have got moles per decimeter cubed times by moles per decimeter cubed. Now that wasn't too bad. Just going to extend the line there. Moles per decimeter cubed, and actually, do you know what? I'm going to be lazy. I'm going to copy, paste, paste, paste. So I've got moles per decimeter cubed times by, times by, times by. So we've got, nope, that was not right. Highlighter, here we go. We've got moles per decimeter cubed, moles per decimeter cubed. We can cancel those out. We've got moles per decimeter cubed, moles per decimeter cubed. We can cancel those out. We are left with moles per decimeter cubed. So we've got a value which is 1 over moles dm to the power of 3 times by moles per decimeter cubed. We've got 1 over moles times moles, so it's moles squared, dm to the minus 3 times by dm to the minus 3 times by dm to the minus 3, so we add those together, so dm to the minus 6. Still not quite there yet. So let's just, so we have then got simplified down, moles to the minus 2, dm to the 6. Not going to go into that in much more detail for you working out units. What I would quite like to get into is how we can then start putting this into practice. So the only way we can really do that is to find an exam question. There we go. Got a nice little exam question, which looks at Kc and units. We've got a reaction that we can work with. So nitrogen monoxide and oxygen react to form nitrogen dioxide in a reversible reaction. We get given it here. Write the expression for Kc for this reaction and state the units. So a couple of things we're going to want to do. I'm going to just highlight it up in different colors so that it's easy for us to visualize. So Kc, remember, products over reactants. So we've got products, the concentration of NO2. Remember here, so there's 2 lots of NO2, so we'd have it to the power of 2 divided by the concentration of NO. And again, there's 2 lots of NO, so it's to the power of 2 times by concentration of O2. There we go. We've got ourselves the expression. What we need to do now is figure out the units. So let's put the units in. Let's rewrite out the expression, but with our units. So we've got moles per decimeter cubed, and we've got that to the power of 2 divided by moles per decimeter cubed to the power of 2 times by moles per decimeter cubed. What we can do here is, let's go for purple. Because we've got moles per decimeter cubed to the power of 2 and moles per decimeter cubed to the power of 2, these presets, let's go for purple, those will cancel out. So we end up with 1 over moles per decimeter cubed. Moles minus 1 dm to 3. There we go. Now that we've got that answer and we're happy with that, shall we try to progress that to make it a little bit more difficult? So rolling on down to here, we've got a bit more of an application question. Now I've left some space around the sides because we're probably going to need to do some jotting down. It is only a 2-mark question, but then as we get down here, we come to a 4-marker. So we're adding that complexity. We're going to do a bit of application of what we already know, and then we're going to actually try and add some more to it. So chemist investigates, mixes together sulfur dioxide and oxygen with a catalyst. We get given a volume here, so let's highlight that up because that's going to be important later on. Mixture is heated, reaches equilibrium without changing the total gas volume. That's important. So that means that this value here is what we're going to come back to, the 400 centimeters cubed. The equilibrium mixture contains 0.0540 SO2 and 0.0270 O2. At the temperature used, the numerical value for Kc is 3.045 times 10 to the 4. decimeters cubed per mole. Write the expression for Kc and the units of Kc for this equilibrium. Now, there's a little bit here that they've given away. I'm not going to tell you what it is. If you can spot it, brilliant. If not, then we'll have a look at the end once we've done these 2 marks. So first things first, it's asking us for Kc and then it's asking us for the units. So let's do Kc first, because once we've got Kc, then we can go on to the units. Kc equals products over reactants, concentration of the products over the concentration of the reactants. So we have got concentration of the SO3 squared divided by the concentration of the SO2. And because it's 2 lots of SO2 squared times by concentration of the O2. Because we've only got one O2, it's just square brackets O2, no indices. Nice and simple. That's your first mark. Second mark comes from the units. So let's move over to the side. We have got concentration squared, moles per decimeter cubed, squared divided by moles per decimeter cubed, squared times by moles per decimeter cubed. Oh, that was a very scruffy 3. We'll just have to live with it. Now, these we can cancel out. We can cancel them out, so we end up with 1 over mole per decimeter. Let's try that again, shall we? 1 over moles per decimeter cubed. Now, we can't leave it like that, can we? So we need to change it back to moles to the -1, dm to the 3, or in other words, dm cubed mole to the -1, or decimeters cubed per mole. Let's highlight up our answers in green. Our answer, this is our answer. Hold on, wait a second. They gave us the units in the question. But we had to go through and make sure that we knew what we were talking about and show that we understood the process. So that's 2 marks. Determine the amount in moles of SO3 in the equilibrium mixture at this temperature to the appropriate number of significant figures. This is a really nice point that we can check back to. It's the maths in chemistry. As we go through the question, we have got 3 sig figs here. We've got 1, 2, 3 significant figs. 1, 2, 3 significant figures. 1, 2, 3, 4. When it says to the appropriate number of significant figures, you have got to go with the lowest number of significant figures given in your raw data. So you've got a toss up between 3, 3, 3, and 4. When you're going through your calculations, keep the values that you have got in the calculator all the way through and then round at the end. And because the lowest number of significant figures given in the raw data is 3, we're going to have to give our answer to 3 significant figures. Scrolling down, we're going to need to use this value, this value, this value, and this one in our answer. That's why we've highlighted them up, so it's easy to refer back to. We've got our Kc. We just need to find out what the concentrations are to be able to substitute them in. So let's work at the top here while we've got all the data. So we need to know the concentration of SO3. We need to know the concentration of the SO2 and concentration of O2. And significantly here, we've got 400 centimeters cubed, or we can convert that to 0.4 decimeters cubed by dividing by 1,000. Now, we don't know what the concentration of this is. We're going to need to work that out before we can then work out the number of moles, the equilibrium amount. We do, however, know at equilibrium, the mixture contains 0.0540 moles of SO2 and 0.0270 moles of O2. So let's put that in. Equals 0.054 divided by 0.4 and equals 0.027 divided by 0.4. Give you a pause if you want to work it out for yourself. Equals 0.135 equals 0.0675. Don't worry, mental maths isn't that great. I have got some notes jotted down where I've already gone through the calculation, just so that don't spend loads of time and all you hear is me tapping away at a calculator. Now that we've got those concentrations, we can then substitute that into our equation. So let's sub these values in. .045 times 10 to the 4 equals concentration of SO3 squared, we don't know that, divided by concentration of SO2 squared, 0.135, 0.135 squared times by 0.0675. So we've now got, we can rearrange it and we get the concentration of SO3 equals 6.120. Remember, don't round, keep your calculator value. That's what I've done. So what we now know is we've got the concentration. We want to know the equilibrium amount. So we're looking at the moles. Moles equals volume times concentration. So we've got 6.120 ... times by 0.4. So n amounts of SO3 equals 2.448 ... but we were asked to do it to the appropriate amount of significant figures. So we've got 1, 2, 3 significant figures. We discussed that earlier. So we've got 2.45. That's our answer. 2.45 moles. Right. Shall we up the ante a bit? Shall we make it a little bit more difficult? Because we've got equilibrium amounts. Same principles apply. Getting the expression in. What they've done is they've, rather than saying, let's do part of the question, second part of the question, they've gone straight in for the 6 markers. So they're asking you, can you put all of this together without any direction? Makes it a little bit more difficult, makes it a bit more challenging, and arguably a little bit more fun. So we've got an equation here. Chemist mixes 0.8 moles of nitrogen, 2.4 moles of hydrogen, and leaves it to reach equilibrium at 300 degrees C. Let's highlight up some information that's important. That's going to be important. That's going to be important. The amount of hydrogen is going to be important. Reaches equilibrium. Volume is definitely going to be important because we need to work out concentrations. And at equilibrium, the amount of ammonia, that's definitely going to be important as well. Calculate the value of Kc under these conditions. Right, before we go any further, if you want to have a go at the question yourself, pause, work your way through, make sure you go through all of your workings. Remember, don't round too early. And then click forward. You can follow the process or you can fast forward me, either which way. So first things first, we're going to need to have a Kc value. Kc equals products, NH3 over concentration of N2 times by concentration of H2 to the power of 3. We need to know the concentrations at equilibrium. It's no good just using 0.8 moles of nitrogen and working out its concentration. That was not at equilibrium. We need it at equilibrium. So I'm going to write it down over here so we've got a nice amount of space to work with, and if we have to run over, we have to run over. N2 plus initial, the change that's undergone, and what it is at equilibrium. 0.800, 2.400, and on. So that's initial. That's when the reaction starts. We've got no ammonia. We've just got the reactants. At equilibrium, it tells us that we've got 0.360 moles of ammonia. So we've undergone a change of plus 0.36. Why on earth have I got that there? There we go. Now we know that the amount of ammonia has gone up. So if the amount of ammonia has gone up, that means that the amount of nitrogen and hydrogen has to have gone down. And that's why we make sure that we've got a balanced equation. That's why we can use stoichiometry. So if it's gone up by 0.36, the nitrogen to ammonia is a 2-to-1. So if that's gone up by 0.36, this will have gone down by minus 0.18. Or in other words, let's use a finer pen, 0.36 divided by 2. Over here, this will have gone down by 0.36 divided by 2 times by 3, which would give us a value of, pause, minus 0.540. So those are the changes. Nice and easy. 0.8 minus 0.8 minus 0.18, getting a bit tongue-tied, 0.62, and 2.4 minus 0.54 gives us 1.86. Now we have got the number of moles at equilibrium. We're not quite done yet because it's not just the number of moles that we need, it is the concentrations. So we've got concentrations of NH3, concentration of N2, and concentration of H2 that we need to figure out. We've been given the volume, 5 decimeters cubed. Concentration equals moles over volume. So we've got 0.36 divided by 5 equals 0.072. amount of nitrogen, 0.62 divided by 5 gives us 0.124, and the amount of hydrogen is 1.86 divided by 5 equals 0.372. Moles per decimeter cubed, molar, moles per decimeter cubed, molar. We now have got values that we can add in. Kc equals, substitute in 0.072 squared divided by 0.124 times by 0.372 to the power of 3 gives us a value of, drumroll please, 0.812. Got our value. We now need units. Let's come back up here. We have got moles per decimeter cubed squared divided by moles per decimeter cubed times by moles per decimeter cubed to the power of 3. Or in other words, we've got moles per decimeter cubed to the power of 2 divided by moles per decimeter cubed to the power of 4. So from that, we then need to cancel. So we would get 1 over moles per decimeter cubed to the power of 2, or moles to the power of 2 dm to the power of minus 6. 1 over those. Then convert that dm to the 6 moles to the minus 2, 0.812 to give us our answer. Sorry, I kind of underestimated the amount of space that I would need there, and I wrote far too big. But hopefully that's helped. As I said, we're not going to go into KP today. We're not going to go into changing conditions. We will go into that in a bit more detail later on. Hopefully that's helped, and yeah, I look forward to speaking to you again soon when we get to go over KP and then on to conditions. Bye.